Welcome to This Explainer. We hear about AI all the time, and it's so easy to talk about it like it's, magic. Like it's this glowing digital brain that just instinctively knows the answers to whatever we throw at it. But today, we are going to completely shatter that illusion. Because AI doesn't just spontaneously generate brilliance. It actually requires mechanics. It needs a rigidly defined, highly structured problem to solve before it can do literally anything. The magic isn't actually in the answer it spits out. The real magic is in how we formulate the problem in the first place.
Think of me as your professor for today's introductory computer science journey. Here's our syllabus for this explainer. First, establishing the vocabulary. Second, problem formulation steps. Third, a water jug tutorial. Fourth, a map coloring tutorial. Fifth, contrasting problem types. And finally, why formulation matters.
All right, let's dive right into Section 1, establishing the vocabulary. Just getting the basics down. So, before an AI can solve anything, we have to translate all our messy human reality into the strict mathematical language of state space representation. Let's look at the foundational building blocks. The very first concept is the initial state. Think of this as setting up the board before you play a game. For example, if you're planning a road trip, your initial state is just your current location. Say, the city of Dang. The AI needs to know exactly where it's starting from before it can calculate a single move.
Next up, we have the goal test. How does the AI actually know when it's finished? It doesn't have intuition, right? It relies entirely on a goal test, which is a specific condition that determines whether the current state is the final desired state. Going back to our route planning example, the goal test is just checking, hey, have we reached our destination of Kathmandu? If yes, boom, the problem is solved.
And finally, we have the path cost. See, AI doesn't just want any solution, it wants the absolute most efficient one. The path cost is a function that assigns a numerical cost to a sequence of actions. It literally sums up the cost of every single step from that initial state to the goal. The AI is constantly evaluating its efficiency, aiming for what we call the optimal solution. That's the one with the absolutely lowest path cost, whether you're measuring total travel time, distance, or even fuel used.
Moving right along to Section 2, problem formulation steps. Let's talk about defining these AI problems.
Now that we've got our vocabulary down, there are 4 overarching steps an AI agent actually takes to formulate and solve a problem. Step 1 is goal formulation, deciding exactly what outcome you want to achieve. Step 2 is problem formulation, which is describing the problem strictly in terms of states, available actions, and the rules needed to bridge the gap. Step 3 is search. This is where the AI explores possible actions and paths to find a sequence leading to the goal. And step 4 is execution, simply carrying out those chosen solution steps in the real world.
Next up, Section 3, the water jug tutorial. Let's look at a state space example.
Okay, so what does this all look like in practice? Let's make these theoretical concepts tangible with the classic water jug problem. It's this famous puzzle we use in CS 101 to demonstrate AI problem solving. Here's the setup. You have 2 totally unmarked jugs. One holds exactly 4 liters, the other holds exactly 3 liters. Your goal? To measure out exactly 2 liters of water. So how would you do it? As humans, we'd probably guess, maybe eyeball it, or just use trial and error. But an AI? An AI cannot just guess.
To solve this, the AI needs a strict transition model, basically a set of allowed actions, or operators. To bridge the gap between having 2 completely empty jugs and having exactly 2 liters, the AI is permitted only 3 specific moves. Number 1, it can fill a jug completely. Number 2, it can empty a jug completely. And number 3, it can pour water from one jug into another, but only until one is either completely empty or completely full. That's it. Those are the absolute rules of physics for this digital world.
Now, what's really fascinating here is how the AI maps this out. It constructs a search tree to use those exact rules. Starting at the very top with an initial state of 0 and 0, it branches out, applying its operators to generate new states. It might fill the 4-liter jug first, or maybe it fills the 3-liter jug first. It systematically explores these sequences using search methods like breadth-first or depth-first search until the goal test, which is having a jug with a value of exactly 2, is met. It's a brilliant, methodical display of exploring sequential actions.
That brings us to Section 4, the map coloring tutorial. We're shifting gears to constraint satisfaction. Unlike the water jug problem, where we cared so much about a sequence of steps, our second tutorial uses a completely different methodology. Take a look at this uncolored map of Australia. In this constraint satisfaction framework, the geographic regions, like Western Australia, Northern Territory, Queensland, and so on, they are defined as variables. And the possible values we can actually assign to these variables, which in this case are the colors, red, green, and blue, are called the domain. The initial state here, it's simply an empty assignment, a blank map.
Now, here is where it gets interesting. The constraint. The rules here dictate the allowable combinations. The primary, explicit constraint for map coloring is that adjacent regions, neighboring territories that share a border, must have completely different colors. For example, if Western Australia is painted red, there is absolutely no way the Northern Territory can be red.
And this brilliantly illustrates the solution. The AI achieves the goal not by finding a path of steps, but by finding an assignment that meets two specific criteria. First, it must be consistent, meaning it does not violate any of those adjacent color constraints. And second, it must be complete, meaning every single variable or region is assigned a value. When both criteria are met, the map is perfectly colored, and our gold test is completely satisfied. All right, Section 5, contrasting problem types, state space versus constraint satisfaction.
Notice the difference here, because honestly, this is the absolute crux of this whole explainer. The water jug problem used state space search. It was entirely focused on finding a valid sequence of actions to travel from point A to point B. The how mattered immensely. But map coloring, that used constraint satisfaction. It really didn't care about the sequence of how we colored the map. It only cared about finding a consistent variable assignment that satisfied all the structural rules. They are two totally different ways to formulate problems for an AI to solve.
Finally, Section 6, why formulation matters. The importance of rules.
So, you might be wondering, why do we even need these incredibly strict definitions, domains, and transition models? Well, because a well-defined problem is literally the only thing standing between an AI and total computational chaos. First, proper formulation ensures solvability. Without it, search algorithms and decision-making models simply have nothing to process. Second, it guarantees efficiency. A tight formulation prevents excessive computation and wild and inaccurate results. And third, it provides measurable outcomes. Goals become specific and time-bound, which allows us to actually evaluate if the AI's performance was successful.
We've seen how translating a puzzle into defined initial states, goal tests, and strict constraints allows a computer to find the perfect solution every single time. It really makes you wonder, if our own messy, real-world human problems were formulated with such strict goal tests and clear constraints, would they be easier for us to solve too? Think about that for a second. Thanks for joining me for this explainer. I hope you walk away looking at problem solving in a whole new light.